Welcome everyone to this year's open house event of the Wanderscher Lab. My name is Andreas Bedov. I'm the communications manager of the lab, and I welcome you to this day to get to know us a little bit better, to get to know what we have been working on over the last year, what our researchers and students are up to, and what we have achieved and what we want to achieve for the next year. We welcome you as friends and sponsors of the lab. So thank you very much already for everything you've contributed over the last year, or maybe even more than that. We will start with a short introduction by Mihaela, and then we go into 3 different sets of talks about different areas of our research and our work. And with this, I will hand you over to our wonderful director, Mihaela, and the floor is yours.
I'm going to give you a brief overview of our lab and give a little bit of context to the day of today. As you know, our lab is very much dedicated to developing cutting-edge machine learning methods to push the frontiers of healthcare. But our work is, of course, more generally applicable in other areas of machine learning as well. I'd like to start by introducing you to our research team, my PhD students and my postdoc. And you see here indicated with a star the 5 PhD students that have joined us this year in 2022. If you want to read more about their backgrounds and how they came to our lab, you can see that on our lab's website under the tab Research Team. Please take a look and learn more about the students especially the students that are not going to present today. I also would like to thank very much to our machine learning research engineers and comms, and I highlighted them here. Also want to say that Evgeny in particular has 2 hats. On one hand, he is an ML research engineer in the Cambridge Center for AI in Medicine, about which I'm going to say a few words later, but also a part-time PhD in our lab. I also would like to highlight with great pride, I'm very proud of the fact that our lab is truly international. We have members from 17 different countries in our lab, and I'm really very, very happy that we can provide this international environment for the best students of the world to come and contribute to research in machine learning for healthcare. Let me start by, again, setting up the scene for our research. Of course, most of you know this very well, but I would like to provide a little bit of context to the work you are going to see today. I always like to start my talks with this statement from Sir William Osler, the father of modern medicine, because it articulates very nicely why medicine is such a complex frontier. If it were not for the great variability between individuals, medicine might as well be a science, not an art. And indeed, we know that medicine is very complex. And this leads to, and this is due to variability between individuals, which leads to different risks over time, variation in symptoms, different health and disease trajectories, and responses to treatment. So the art of medicine has been, over the centuries, to make judgments on the basis of this very complex information about the patients to better manage them. So what we hope to do in our lab is to develop cutting-edge machine learning methods to empower an entire healthcare ecosystems, clinicians, patients, and everyone involved in providing better care for patients. And we hope that in this way, we can turn, using machine learning, the art of medicine into a science. We see numerous opportunities that machine learning can provide in changing and revolutionizing medicine by delivering precision medicine at the patient level, by understanding the basis and trajectories of health and disease, by empowering healthcare professionals and patients, by informing and improving clinical pathways, enable better utilization of resources and reducing costs, transforming population health and public health policies, and last but not least, enable new discoveries, both clinical as well as new therapeutics. And indeed, the research in our lab is aimed at developing such machine learning techniques that can address these opportunities that I have outlined. We divide our research in 4 different groups or categories. And today you are going to see research in all these 4 areas. On one hand, we know that in order to build high quality machine learning analytics, we need to focus on the data that is used for developing this analytics. So today you are going to hear quite a lot about our work on data-centric machine learning. We also do research on generating synthetic data. Today, I'm not going to talk about this, and my students will not talk about this, but our lab has done significant work in this area, and I'm going to point you out in a little bit to some of the recent endeavors in this particular area. We also develop, in the blue box, a lot of cutting-edge analytics. For instance, estimating treatment effects at the personalized level, causal deep learning that can lead to new discoveries, time series forecasting, automated machine learning, transfer learning, active sensing, and many others. Today, you are going to hear about a quite large number of recent analytics that we have developed in our lab for individualized treatment effect inference, for causal deep learning for discovery, for time series forecasting. But these analytics cannot be used in the clinical setting unless they are interpretable and robust. So in our work, we do quite a lot of research on making black box machine learning models interpretable and trustworthy. You are going to hear talks today that are going to talk about interpretability especially. Finally, we do not view these analytics as operating alone. They are going to be used by clinicians and patients to improve the management of care for patients. So we develop technologies that enable humans and machines to form powerful partnerships to address complex problems in medicine, thereby augmenting human skill. You will not hear too much about this today, but we hope to present you more work in this particular area, hopefully next year. The structure of today's sessions will be as follows. We are going to have 3 sessions, and I divided them in 3 categories. The first set of 3 talks is going to focus on challenges. What we see as new areas that are challenging existing wisdom and where we believe that there are great opportunities. And you are going to hear today about our work on data-centric machine learning from Nabeel, causal deep learning from Jeroen, and sequential decision-making in clinical trials from Alihan. Then we will move in the second part of this day on the growth area, where we really are aiming at creating new areas of research, but also cultivating underdeveloped areas. And these are areas where we have already done some work and where the research community has done some work, but we believe that some very new ideas have emerged in our lab in the last year that we would like to present to you. And we feel that this is not the end of the story, but rather a growth area. You are going to hear in this particular stream of presentations from Alicia about personalized therapeutics. You are going to hear about next generation time series models from Zhaozhi and individualized treatment effects over time from Fergus. Finally, in the last stream of presentations, we are going to provide projects that we feel are really ready to grasp by the industry and industrial collaborators, and we believe that they can make an immediate impact on development of these technologies in healthcare. You are going to hear from Alex about synthetic model combination and applications to pharmacology, including a collaboration we have recently had in this area with AstraZeneca. Then we are going to hear from Jonathan about machine learning interpretability. And finally, we are going to discuss together with Rob our current very comprehensive GitHub for machine learning interpretability, and also provide you with a demo. These different threads are going to be interspersed with time for breaks and questions. Let me tell you a brief overview of our research in the past year. Past year has been a very successful one for us, and we are really very proud that the lab has collectively presented and is going to present a large number of papers at the best venues in machine learning, NeoRIPS, ICML, and iClear. You can see these papers on our website. And you can look at these publications under the Publications tab. In addition, we also have published papers at a large number of other venues, inclusively AI Stats and AI, as well as journals. Also, I would like to highlight that we have organized and are driving together with some of our collaborators 2 workshops at NeoRIPS 2022. One is going to be on causality for real-world impact, together with Microsoft Research, who is also a sponsor of our lab. And the other one is on synthetic data for machine learning, which we also have organized together with another sponsor of our lab, AstraZeneca. Please take a look at these 2 workshops, and you can see how our research is both supporting but also shaping these 2 areas. As you may know and you may be familiar with, we also have started 2 years ago a set of engagement sessions that we call Inspiration Exchange. And they really are focusing on creating a community where we can discuss about cutting-edge machine learning for healthcare. But it is only relatively recently, in May of 2022, that we have started to invite experts from the research industry to come and join us and discuss about these topics and give us food for thought and feedback on the research. We have had quite a large number of sessions since May that have focused on a variety of very interesting topics. If you are interested in seeing the research progress on a more continuous basis rather than just coming to these annual open houses, we invite you to join us in our engagement sessions, Inspiration Exchange, either live or potentially watch them afterwards because they are on our YouTube channel. If you are a sponsor of the lab and you would like to participate in these sessions as an invited guest, please drop me a line and we would be delighted to invite you in a session that's pertinent to your research interests. Also, 2 years ago, we started another engagement session together with clinicians that we call Revolutionizing Healthcare. We have by now more than 500 plus clinicians from 5 different continents engaged with us and trying to work with us closely to understand the problems they need solving and try to articulate the challenges, but also the opportunities in healthcare. So we are not inventing ourselves problems in healthcare, but rather working closely with clinicians to understand the healthcare ecosystems, the opportunity, and what we can do to empower them. These sessions are only open live to clinicians, but you can view all of them online afterwards, offline afterwards on our YouTube channel. And some recent sessions that have been extremely interesting have involved machine learning for clinical trials, machine learning for specific diseases such as cystic fibrosis, etc. Please take a look. Even more recently, just in March 2022, we started an engagement session dedicated to women, the focus being to inspire female students and young professionals to join this vibrant area of machine learning, engineering, computer science, applied math. And the reason we started as a lab these sessions is, as you can see, the lab currently has just one woman PhD student present in our lab, and we really hope to increase the participation in this area and hopefully over the years recruit more women and inspire in general women to really consider this very creative field of machine learning. We also have prepared over the years a set of tutorials that you can engage with. We, of course, do a lot of research in a large number of areas, but as a side effect of this, we need to have a very good understanding of cutting-edge work in a variety of topics. And for that, we have developed resources which you, the sponsors of the lab, have access to. So one is tutorial series, which we have done already last year, but which I would like to still highlight, which represents a very comprehensive set of lectures given by a variety of students in the lab, focused on estimating treatment effects, estimating individualized treatment effects, and presenting a variety of solutions that exist, and in addition, which our lab has developed using machine learning. Also, we are giving tutorials at a variety of machine learning conferences. In past years, we provided tutorials at iClear, at ICML, and many others. In 2022, together with Fergus, I have given a tutorial for AI 2022 on machine learning for time series. If you are interested, please take a look. This tutorial is online. And at the next 2023, I'm going to give not only a tutorial, but also a lab on synthetic data using machine learning together with Zhaozhi. So I hope you can join us either for the AI itself or afterwards viewing the resource. More generally, all these tutorials can be found on our website under tutorials. If there is a particular area that is of interest to you, where you would like us to develop a more tutorial resource, please drop me a line and we can work together to develop this tutorial for you and for your company and for your needs. We also have on our website a special tab dedicated to impact. As I mentioned, we work very closely with clinicians in a variety of fields: cancer, Alzheimer's disease, ICU, and very importantly for us, cystic fibrosis. So please take a look at the different areas where the lab has very close collaborations with clinicians and charities, and trying to develop research to support patients with these particular diseases. We also try to not only develop methods and write papers, but also provide high-quality software that can be used by you to try in your own companies or your own organization. You can find this software in our GitHub, and this is quite well organized. So I invite you to please take a look there. I'm also going to give a little bit a note that on Monday next week, for the first time, we are going to issue a new version and a much improved version of an automated machine learning method for risk prediction. You may have heard, if you followed our lab, about our initial version of autoprognosis. But now we are going to issue a much improved version of that, which can be used for clinical analytics at scale. So please follow us and please follow the announcements which are going to follow next week. The software that's associated with this is going to be very robust and very comprehensive, and we believe to be the largest academic software that is going to be publicly available in this area of machine learning for healthcare. As you know, we have this symbiosis between our lab today you are a guest of our lab, but I'm also director and founder of the Cambridge Center for AI in Medicine. And at times the question arises as to how these two organizations interact. The Van der Schaar lab is focused very much on developing cutting-edge machine learning methods in machine learning for healthcare by challenging conventional thinking, cultivating new areas of research, and defining and exploring new areas of impact, while CCM is much more focused on really creating a disruptive effect in medical, biological, and pharmacological settings by adopting these cutting-edge machine learning methods and applying them to really push the frontiers of bioscience, medicine, and more general pharmaceutical industry. This brings me to the final slide of my presentation. So again, I look forward to the talks and to your comments on these various talks. After every thread of this particular set of presentations, we will have 15 minutes of Q&A. Please, already during the talks, put questions in the chat and we will take them one by one and the students are going to answer them. Thank you very much again for making time out of your very precious schedule to really join us today. And thank you very much for your support of our lab.
And we will start with our first talk, which will focus on data-centric machine learning. And our first student up is Nabeel.
So hi, good afternoon, everyone. So my name is Nabeel Seedat. I'll be talking about a data-centric AI lens and how we believe this can enable robust and reliable machine learning systems. So for the better part probably of the last decade, we've probably all heard a lot of this hype of data being the new oil. And I think over this last decade, there's been a lot of focus on the utilities of this. And we really believe that there needs to be more of a push on actually building these oil refineries for data, where right now we are able to extract a lot of raw data, we are able to get access to it. And right now we take a lot of this raw data and feed it to machine learning systems to gain insights, to make predictions, to make forecasts. And we believe that the big missing piece of this jigsaw is right in the middle here of how can we build systematic data refineries? And for this here, we need some sort of data-centric lens to fill this gap. And where current approaches to machine learning really view data often as some sort of fixed asset, which is very much external to the model building process. And a big focus is largely on model iteration. How can we build new models, better architectures, optimize better loss functions, or even build better optimization algorithms? And while we do still think that model iteration, of course, is still fundamental to research and improvement, we tasked ourselves with saying, how can we actually make data take a bit more of a center stage and bring data processing to a more systematic format? And for this, we need data-centric AI. And by this, we mean data iteration somewhat becomes more of a focus, and we aim to build systematic tools for data acquisition, data cleaning, auditing of data sets, as well as generation of data sets. And we believe that by improving the quality of all of these and making them more systematic, we can thereby improve the performance even on standardized model architectures, whether it be your neural nets, boostings, transformers, etc. And just to make it slightly more concrete, we view data-centric AI as encompassing methods and tools to systematically characterize, evaluate, and generate the underlying data used both to train machine learning models as well as to evaluate said models. And over the past year, we've aimed to tackle a broad bit of this challenge. And we started first with a paper, Data IQ, where we aim to characterize the data for higher quality training data sets. And then we focused on a second paper called Data Suite, where we said, can we evaluate the data to understand when you can actually trust models' predictions? I'll focus mainly on the second one, but briefly at the end, touch on Data IQ. So in Data Suite, where we focus on data-centric identification of in-distribution incongruous examples, this was joint work with my brilliant co-authors, Jonathan Crabbé and Mihaela van der Schaar. We presented this at ICML 2022. And we thought about the problem that currently in machine learning, a big portion of the literature focuses on largely on out-of-distribution detection. And of course, this is an important problem to be solved, However, a much less understudied yet equally important problem is how do we actually even assess data that lies within distribution, and where within this distribution we might have heterogeneity across the feature space. And just to anchor things before diving into methods, we thought to ourselves, we have two data scientists, Alice and Bob. They both exist at different stages of the machine learning model development pipeline, where Alice exists at data exploration, really wants to understand uncertainties and inconsistencies in data, whereas Bob wants to have a machine learning model already, has trained F-star and wants to understand when the predictions can be trusted. And most work has fundamentally really focused on Bob's use case without really saying, how can we package these two together? And we aim to address this. So we introduced Data Suite, but before jumping in, current approaches to machine learning have largely looked at how can we model uncertainty on a predictive level? How can we understand when models are uncertain in making predictions? And we call this model-centric uncertainty. And one can think of this as Bayesian neural networks, Gaussian processes, quantile regression, any of the like, where the uncertainty is highly dependent on the model itself. In Data Suite, we take a paradigm shift and we model uncertainty in the data itself, and more precisely, uncertainty in the feature values. And the nifty or nice property that this imbues is that we're able to understand which examples are uncertain from a data perspective, and we do this independent of the downstream predictive model. In order to achieve this, of course, we need some principled goals. And in Data Suite, we built feature-wise confidence interval estimators, and we use these estimators to characterize new instances based on a set of training instances, with the goal of achieving a characterization of the data set, as you can see on the screen right now. And these confidence intervals obviously need certain properties. We want them to have nice coverage guarantees such that the true value lies within our predicted intervals with certain guarantees. We want them to be adaptive on a feature-wise level such that we can identify which features we are most uncertain about. But we also want them to be adaptive on an instance-wise or sample level such that we can order samples in a data set from most certain to least certain. And we want to do this decoupled from a downstream predictive model. To achieve this in Data Suite, we take a pipeline approach where we start with a generator, which uses copular modeling to produce an augmented dataset dtrain plus. And the nice property of this is that it allows us, in cases where privacy and data sharing is a concern, to no longer need access to even the true original training dataset. And on the basis of this augmented dataset, we then just simply can learn a representation function. And then using this representation, what we do is we build feature-wise conformal predictors in order to produce the intervals, which I show below. And these intervals, on the basis of conformal prediction, are then used to flag instances as both being uncertain or inconsistent based on the type of interval we see. If they're very large, we consider them uncertain. If we have the true value actually lying outside of our predictive interval, we say they are largely inconsistent. However, now that we have this, you might be asking, what can we actually even do with these intervals that we provide? So in Data Suite, we can enable reliable model deployment. We can confidently use Data Suite because we have 1 minus alpha coverage guarantees, which are both theoretically motivated as well as experimentally proven. We also show that we can improve downstream model performance, where the stratification using these intervals are improved over stratification using model-centric counterparts. And in addition, this is done in a model-independent way because we can consistently find impactful instances for a diverse class of downstream predictive models. Now, harking back to Alice's use case around data exploration, as you can see on the screen, we're able to also identify certain groupings within our dataset, where green highlights the certain classes and red the uncertain. And these highlight specific demographic groups within the dataset, where actually a data owner might want to understand this and then take action to improve the dataset by perhaps doing targeted data collection in these more uncertain regions. Now, briefly, before ending this presentation, I briefly want to just describe Data IQ, which is this joint work with, once again, Jonathan Crabbé, and then Iwana Bika and Mihaela, which we'll be presenting at NeurIPS 2022, where the broad goal was to say, how can we better characterize training data sets? And for this here, we actually studied the dynamics of how individual samples evolved through a model training process. And we use this to characterize a data set into examples which are easy for models to learn, examples which are ambiguous, and we might actually want to collect more features for these examples, and examples which are just intrinsically very hard for models to predict, such that people can actually understand at a sample level how these different examples play a role to a machine learning model. We also provide a framework which is very usable for neural nets, as well as XGBoost, such that it's usable across a wide variety of modalities. In the paper, we do study prostate cancer and COVID from a clinical perspective, but however, for the purposes of this, I'll be presenting an example beyond tabular data on an image case, simply because it's more illustrative. So we take a task of actually predicting gender of from an image, and we find that the easy group, as you can see on the screen, corresponds to predictions from the Celeb A dataset that might be more obvious to a machine learning model and were easy to learn. On the ambiguous case, we found that images of females with shorter hair were often considered ambiguous, images that were blurry, or images that were often obscured. And what we feel that this allows, it allows people to understand fundamental limitations in datasets, as well as where models are latching onto spurious correlations in datasets themselves. And we feel that this is a useful tool for people to be able to actually audit these type of issues in their data. And lastly, the hard examples. These are examples actually where we note the incorrect ground truth label, and it provides a way for practitioners, or anyone for that matter, to actually understand and find out where we might have mislabeling, even in large-scale datasets. So we see huge utility, particularly on the ambiguous and hard groups, to really understand the data that's being fed to these downstream models. I hope that you do engage with these two papers and broadly to this data-centric agenda. And I'd really like to thank our sponsors, without which none of this research would have been possible. Thank you.
My name is Jeroen, and I'll talk about causal deep learning from the setting of scientific discovery using differentiable structural learning, which is a paper co-authored with Nabeel, Fergus, who will give a talk later, and Mihaela, of course. So scientific discovery is obviously an important problem, right? With scientific discovery, we aim to infer if variables are related, yes or no. And we can do this using basically three very high-level steps. And the first step is we formulate an hypothesis using some observational data. Like we think A is perhaps associated with the variable B. Next, if we have formulated a hypothesis, we go gather some experimental data in hopes to confirm this relationship in step 3. So with this experimental data, we will reject or accept our hypothesis. Now, with this paper or with this problem I'll discuss today, we're focusing on step 1 in particular. So from observational data, imagine some data set, we propose a set of hypotheses that we can later test using this experimental data. This is a very important problem, and there's a very simple reason why this is such an important and exciting problem. If you have more variables, the number of hypotheses you can come up with explodes. There's a super exponentially large set of potential hypotheses you can relate with these many variables. So creating experiments for all potential links is simply impossible. So with this work, we want to reduce the set of hypotheses to a number that is actually tractable to create some experiments with. So where are we today in this quest of formulating hypotheses? There are many methods that do this already, and one is of note is this thing called no-tiers that people have introduced a couple of years ago. The reason why no-tiers is such a nice method is it is a differentiable method that is incorporated in many existing machine learning models, including some of our own labs, such as Causal and Miracle. Now, while no-tiers is super nice, it also has a major flaw, and that is no-tiers is not transportable. So, and transportability being actually an element or a property that we would like to have with differentiable structural learners. If we want to use no-tiers for scientific discovery, we would like to be able to generalize our discovery beyond this data set that we happen to have. And this is what we mean with transportability. So we formulate, or what does this hypothesis look like, is we formulate basically a hypothesis as what we call a directed acyclic graph. And this has a couple of advantages. First, it's clear how we can set up an experiment. For example, if the DAG, directed acyclic graph, says that A is causing B, we only need to change A to see if B is actually changing with it. For example, if we set up an experiment where we change B, we hope that A doesn't change with it. And if it doesn't, then we sort of confirm our hypothesis. Beyond that, DAGs also encode a bunch of other properties of the distribution itself, such as independence or conditional independence. Furthermore, beyond like independent statements, there's a lot more additional theory we can tap into if we have a DAG at our disposal. This is actually a very well-studied topic in graphical modeling. This is what a DAG looks like, right? So from this DAG, we learn that A is causing B, B is also caused by C, B to D, and so forth. So it's this type of set of hypotheses that we would like to end up testing with experimental data. For example, if we want to see if D is actually causing E, then we can set up an experiment where we modify D a little bit and see whether E changes with D or not. With respect to transportability, right? So we can formulate the first step, if you recall, coming up with this hypothesis as like the most simple mathematical formulation, where we translate a data set D into a graph G. This is basically the objective of a recent paper. It's a very simple thing, but there are some caveats to this. It's quite tricky to do this technically. Having more data requires very efficient optimization. So we need a differentiable model. So we base ourselves on notice for this. And we can use, if we have a differentiable model, we can use gradient-based optimization, which is basically what most modern machine learning methods would use. We should also have a structure that is transportable. So what do we mean with transportability exactly? Imagine a population of patients, for example, all the patients in England. We have different hospitals. We have one located in London and one in the rural area of England. And each hospital has their own data set of patients. But because all patients have age and blood pressure and all these other variables, the same data sets would collect the same variables. But it's possible that these data sets are differently distributed. For example, London may host younger patients and the rural area may host older patients. But that shouldn't matter if you want to make some scientific discovery, right? Blood pressure should always relate to heart condition. So if we learn a DAG from the red data set or a data set in London, it shouldn't matter if we learn a DAG in the rural area because these DAGs should be the same. This means that the DAG learned from London is transportable to the data set in the rural area of England. This is a thing that is completely overlooked by any differentiable structural learner at the moment. So these seem to be mutually exclusive, right? Having an efficient optimization, we should also have transportability. So how are we actually doing this? So let's focus first on the simple case where we actually have multiple data sets. I know it's a bit unrealistic, but it's easy to reason about it this way. What we do is we'll learn a separate structure for each of the data sets. So in this case, we have K data sets. We learn K structures. And what we do is we learn the structures without knowing anything of the other structures. But as a final step in this green thing, we backpropagate basically the difference between all these structures that we've learned separately. So to recap, we learn a structure on each data set by optimizing the differentiable score function. And in our case, we use no-tiers MLP, but you could plug in anyone. And we compare them and make them look the same by also optimizing the mean squared error between the adjacency matrices of the structures. So that kind of works, but what if we only have one data set, right? Well, it turns out that we can also make this work with our special subsampling routine. So what we do is, if we only have one data set, we can artificially create multiple by subsampling them from some known distribution that we define. What this would look like graphically is, imagine a data set on the left with all these black circles. We can sample or resample these black circles using these, in this case, Gaussian distributions that will result in differently distributed subsets while still retaining the properties that we need for learning a transportable structure. So does this work? Well, yes, so it works really well, actually. When we compare our method that uses node tiers with the original node tiers on the experiments that are presented in the node tiers paper, we seem that to improve quite a bit on the default node tier setup. So in this case, each row is a different type of underlying graph, and each column is a variable in this graph that we change. For example, n is the amount of samples we give them, s is the number of expected edges each graph has, and the metric is the structural Hamming distance. So lower would mean we propose a graph that is least different from the underlying ground truth graphical model. Furthermore, and this is quite interesting, our method called destruct seems to decrease computation time quite a bit, sometimes up to 20 times faster than original node tiers. And the reason we believe is that node tiers doesn't cope very well with large data sets, which is not very useful if we want to do something really interesting. Beyond that, we have like quite a bit of experiments that you may find interesting in our paper. So I would like to point you towards that. So, okay, great. We have a neat method. How can you actually use this in your setup? So there are two ways you can use destruct, and it's the direct way or the indirect way. And with direct, I mean, with destruct, we can inform practitioners to perform clinical trials, for example, like which of the variables are actually related to the outcome rather than assuming that every variable is related to the outcome. You could do feature selection with this, identify which variables are important for prediction. You could set up experiments. So with some observational data, we'll learn some links. We can then inform ourselves with how should we set up our next experiment. You could identify bias, for example, and much more. And then there is the indirect case, where destruct can be used to enhance methods. For supervised learning, Causal did this. This is a paper from the lab some years ago. Causal did this with the original node tiers. But since destruct is equally differentiable, you could just plug in destruct and see how Causal will improve from this. The same for Miracle, where node tiers was used to do imputation, but also for causal discovery or representation learning. Now, the indirect case, I believe, is quite interesting because this is what we call causal deep learning. Right? We would use knowledge gain from structural learners to enhance basically deep learning methods. So with that, I'd like to end with some links. The most prominent one is the research pillar I wrote with Zhaozhi and Mihaela on causal deep learning. This is on our website under research pillars. Furthermore, I would also like to point you to the code base of destruct as well as the link to our paper. I'd like to also thank the many sponsors that made this work possible, such as Cystic Fibrosis Trust and WD Armstrong Trust. Thank you.
Hi everyone, my name is Alihan. I'm a PhD student in the Vandashar lab, and I'm going to present you sequential decision-making in clinical trials. In particular, I'm going to talk about one sequential decision-making problem that we have recently formulated in one of our recent papers called When to Make and Break Commitments. So to start off, the current standard, the gold standard of running clinical trials is randomized controlled trials. These are usually conducted to show efficacy of some newly developed treatment. Although their status as the gold standard for evidence-based medicine, there are several recognized problems with them. And the problem that I'm going to focus today is the inflexibility of their design. In particular, when you run a randomized controlled trial, you need to specify what population you are going to target beforehand. And until the trial is concluded, it's not possible to adapt this population based on the new data that was observed during the trial itself. And this could be problematic And to see how I have this kind of motivating scenario. Suppose we have a treatment that is effective only for a particular subpopulation of patients, but when viewed for the overall population, the treatment is ineffective. So in a scenario like this, if you run a randomized controlled trial that targets the overall population, it is highly likely that it will fail, and the result, the treatment would be denied for the subpopulation who would have actually benefited from it. So in this case, it's important to have some sort of adaptive design that can select the target population based on the data that is observed during the trial. And so in short, RCTs are limited in terms of when and in which aspect they can be adapted. And there are several adaptive experiment designs that aim to address this. The most common or most popular would be adaptive enrichment and adaptive signature designs, where as the trial goes on, it's possible to determine the subpopulation that is focused on, but this adaptation can only be done during the fixed decision points that are determined before the trial starts as well. And usually only one interim analysis is considered when applying a design like this. And again, related to this story, there are also randomized controlled trials with futility stopping, where it's possible to stop the trial in any time, essentially. But here, the decision is only restricted to either stopping the trial completely or continuing with the original trial without the possibility to select a subpopulation to focus on. And in this work, we define a new strategy called optimal commitment, which can adapt the trial possibly at any time and can also choose among many subpopulations when deciding which population to target. And the way we do it is we essentially view experiments as commitments. And what I mean by a commitment is that consider a randomized clinical trial that is launched according to some pre-specified design. And how it will go on is that at each time step, a new patient will arrive. You will see outcomes for this patient. And at the end of like a predetermined number of samples, we run some sort of hypothesis test to see whether the experiment was successful or not. And we say this requires commitment because of three reasons, essentially. First, there's usually continual costs that are being incurred while doing this to be able to keep the experiment running. For each population, for each new sample, we need to dedicate some sort of financial resources as well as some time resources. Second, the reward that is going to be received from the trial is only received at the very end of the trial if the trial is completed. And it's uncertain whether that reward will be achieved or not, because it depends on the success of the trial as well itself. And third, it's not possible to modify this design on the fly. So to gain any sort of benefit from an experiment, somebody needs to commit to incurring all this continual cost for that possibly uncertain reward at the end. And this naturally brings up a sequential decision-making problem as a result, which we call the optimal commitment problem. And the problem here is, at what point the data that we collected so far tells us that stopping the experiments is the reasonable thing to do, to avoid future costs that will be incurred, but also at the same time forfeiting any kind of reward that can be received at the end. And if it's reasonable to stop the trial, then which alternative trial that we can start instead that will be actually more likely to provide returns for us. And that's what we call the optimal commitment problem. And the key insight in solving this problem is that whatever policy we use it needs to be optimistic in some sense, meaning it needs to prefer continuing ongoing experiments, although they might seem unlikely to succeed at the time. In more technical terms, consider a greedy approach that stops the trial immediately if the expected reward that is going to be received at the end is less than the costs that will be incurred. And in certain simplified cases, this translates into stopping whenever our test statistics gets below a certain time varying threshold. And when we analyze this simplified setting, we see that the threshold that needs to be adhered by the optimal policy is lower than the threshold that the greedy approach dictates. Or in other words, there are cases where the greedy approach would prefer to stop, whereas the optimal decision would be to continue despite the fact that the trial seems like it's not going to provide any return at the end. And of course, this insight is gained in a like very simplified scenario, and the challenge is to kind of generalize it to the more complex version of the problem in general. And to be able to do that, we propose a Bayesian algorithm that essentially keeps a Bayesian posterior for each individual subpopulation's posterior. Then using those posteriors, we identify a candidate experiment that we might potentially consider replacing the ongoing experiment with. And this requires us to do a combinatorial search over all the possible combinations of populations that we might consider as targets. And then once we have our candidate, then we need to compare it against the ongoing experiments to decide which will have the best return for us. And when we are doing that, based on our insight, we actually put the burden of proof on the candidate experiment as well. It needs to be much more likely to return a positive reward at the end to be able to replace it with the ongoing experiment. And here are some like basic results. Since each of the kind of alternative trial designs that I talk about favors different ground truth instances, we look at the average utility, the utility achieved by them when average over all kind of interesting instances that we could have. Here we consider green instances where the treatment is effective for the overall population. We consider amber instances, which is very much like the motivating scenario I talked about at the start, where the treatment is only effective for a particular subpopulation, and red instances where the treatment is straight up ineffective. And just to give you an example, a randomized controlled trial would favor green instances here because it would target the overall population. And in any other instance, it wouldn't be possible to adaptively change that. And when we look at the results, biased OCP achieves the best utility when average over all instances, and it's particularly thanks to it achieving a better balance between all these different instances. If you are interested about more details, I would highly encourage you to take a look at our paper, as well as our research pillar in our website that talks about our other work on clinical trials. Thank you very much for listening.
Hi, my name is Alicia. I'm starting my third year as a PhD student with Mihaela now. And I will be presenting our work on interpretability, or on benchmarking heterogeneous treatment effect models through the lens of interpretability. We will be talking about interpreting machine learning methods for estimating individualized treatment effects, also referred to as ITEs. And as I probably don't have to tell most of you, estimating personalized effects of treatments is a really complex problem that's inherent to many fields, and especially important in healthcare. When we have different treatments or other types of interventions that we would want to give to a patient, but we want to make sure that it works for that specific patient. Because of this, the machine learning literature in the recent years has proposed many very sophisticated but opaque treatment effect estimators that are some kind of black box machine learning method that outputs an effect estimate simply as a number. Our lab has done lots of work on this, specifically in my PhD as well. But all of this has been very black box. And when we evaluate this, we usually evaluate it in terms of the root mean squared error of estimating the underlying effect function. So we simply compare the effect estimate outputted by the black box to the true effect and see how close they are. But in this paper, we kind of argue that this is not enough. And instead, we'd like to think about what we've actually learned from this black box. So an ITE estimate is really not always the ultimate goal. And often we would wish to derive some kind of more actionable insight from it. For example, we'd like to have some kind of scientific discovery and know more about what are the drivers of effect heterogeneity. This can be used to find groups or biomarker signatures with enhanced effect, or to find groups or biomarker signatures for whom a treatment doesn't work, and it's better to be excluded from trials or further prescription. So in this paper, we ask a simple key question, namely, do existing treatment effect estimators discover the true drivers of effect heterogeneity? To do so, we investigate how to use feature importance methods to interpret black box ITE estimators and use this to evaluate them on the new task, namely their ability to discover drivers of heterogeneity. We then propose a benchmarking environment and provide new insights using this into the performance of existing ITE methods. So to kind of set the scene, we're considering a treatment effect estimation problem where each individual is characterized by a potential outcome with treatment and a potential outcome without treatment. In this setting, a treatment effect is defined as the expected value of the difference between outcome under treatment and outcome under no treatment. So let us now look at how to interpret heterogeneous treatment effect estimates. Interpreting treatment effect models is different from interpretability in a supervised learning context. Here, when we say interpretability, we consider the setting where we wish to know what covariates does my machine learning black box pay attention to. It's different from the supervised learning context because in treatment effect estimation, there's actually two types of important covariates. On the one hand, we have prognostic covariates, which are those that influence outcomes regardless of treatment or regardless of treatment assignment. These are common risk factors, such as, for example, age, which affect both potential outcomes. On the other hand, we also have predictive covariates, which determine the differential responses to treatments. And these are drivers of heterogeneity, for example, hormone receptor status in cancer settings. And these are covariates that affect the potential outcomes differently. So here we argue that predictive covariates are obviously of most interest when interpreting the learned treatment effect functions, because predictive covariates are those that actually determine heterogeneity in this treatment effect that's estimated. The problem is that many black box treatment effect estimators actually do not have really a built-in measure to detect which features are paid attention to. So to tackle this, we simply use off-the-shelf feature importance methods, which we refer here to as A, to assess whether a treatment effect estimator has learned that a specific feature is predictive. So we basically wrap this, this feature importance method around our treatment effect estimator in a standard way, and then look at the importance, which increases with the absolute value of our feature importance method's attribution score. And to do this, we could use any type of attribution method, for example, integrated gradients or Schaar. The key question that we'd like to answer by doing so is whether estimators pay attention to the correct covariates. And we measure this in two ways. On the one hand, we measure what we call the predictive attribution, namely the proportion of importance correctly attributed to the predictive covariates. So here, the higher this is, the better. And we also look at the prognostic attribution, which is the proportion of importance incorrectly attributed to prognostic covariates. So covariates that actually don't matter for the treatment effect, but only matter for the outcomes, but in the same way. So for this, we'd like it to be lower. And we measure this, we'd like to measure this on a benchmark. However, for treatment effect estimation, we actually have a problem. And this is well known. It's called the fundamental problem of causal inference. That's that you can never use real data to truly evaluate treatment effect estimators because you only ever have one of the two potential outcomes available. So it's become kind of normal in the treatment effect estimation literature to use simulations. And that's something that we also have to rely on. But here we have an additional problem, namely that we not only don't have the potential outcomes available in real data, but we also never know what the true important covariates are. So because of this, we design a benchmarking environment, which is semi-synthetic in that it uses real covariates, but simulated outcomes and treatment assignments. And this assures that we not only have ground truth labels under both outcomes available for each patient, but it also ensures that the covariate classification is known by design. And so this benchmark kind of serves as a test bed or some kind of wind tunnel environment where we can have a very flexible DGP that allows us to study the effect of interesting experimental knobs. So we can vary dimensions of interest in the data generating processes to see which of the estimators are robust to this. So in our paper, we conduct extensive empirical studies using the metrics that we defined and this benchmarking environment, and that brings us new insights on these different estimators. So for example, here we compare different types of black box estimators based on neural networks, as we vary how strong the predictive effects are relative to prognostic effects. Here on the x-axis, the further you go right on the x-axis of these plots, the further, the stronger the predictive effects are. And we plot here the correct attributions of importance to predictive effects. And as we see, the stronger the predictive effects, the better all methods do. And conversely, when we consider how much attribution is incorrectly attributed to prognostic effects, we see that the stronger these effects are, the less misattributions are made. Finally, we also compare just how these different methods do in terms of RMSE, so just in terms of estimating the underlying numbers. And we see that our attribution metrics give slightly different conclusions than when you just look at the root mean squared error. So overall, we conclude that, for example, the strength of predictive effects really matters in determining how well different methods do at recovering true predictive covariates, and some learners seem to do systematically worse than others. Also, using attribution metrics leads to interesting new insights relative to considering only standard RMSE metrics. And conversely, performance in terms of RMSE does not necessarily translate into good discoveries. In our paper, we also additionally investigate the effects of the degree of nonlinearity underlying the potential outcomes, and the type and degree of confounding. So to conclude this, we found that benchmarking K estimators along a new dimension, namely in how well they do at recovering different types of covariates, brings interesting new insights. We think in the future it would be interesting to investigate even more learning strategies in different Bayes methods. So we only considered neural networks, but there's many more methods that could be used to implement different learning strategies that could be considered next. Based on the findings that we've made, it would be interesting to consider whether we can design better methods by taking these findings into account. And finally, it would be interesting in future work to consider whether there are other neglected dimensions that such estimators should really be benchmarked upon. So the paper will be presented at NeurIPS as part of the benchmark track later in December. If you want to have a look, the QR code on the slide leads to the paper. And finally, if you're interested in more generally our work on ITE inference, we have a pillar on our website that's dedicated to all our older and more recent work on individualized treatment effects. Thank you so much for listening.
Yeah, thanks everyone again for engaging in today's session. Today I'm going to talk about neural Laplace, which is a work that is jointly done by Sam, me, and Mihaela, and it is accepted in ICML this year. I just want to briefly mention that our lab has made many contributions in time series analysis, and you can see our website for more comprehensive introduction of all the methods we have developed so far. But today we're going to mainly talk about neural Laplace, which is our latest work on neural differential equation. So a key problem in medical time series, especially time series in EHR, is that the patient's information are observed sporadically and with very irregular intervals. And in deep learning literature, the recurrent neural network contains many popular and powerful architectures. However, they are designed to operate in discrete time only, and they can only handle regular observation. And this is because the internal state of recurrent neural networks is only updated at regular intervals. And this means these states are constant between observations, which is not true in reality. So later, after recognizing this problem, researchers have developed several new architectures to fix this limitation. And examples include GRUD and phased LSTM. And these architectures employs a temporal decay function to model the change of states between two observations. However, the functional form of these decay functions is pre-specified, usually simply using an exponential function, and often involve a fair amount of handcrafting. So the latest development in deep learning time series model is neural differential equations. And this work is pioneered by Neural ODE, which is put forward in 2018. So the class of neural differential equation models enables continuous time model by design, is essentially modeling the continuous dynamic as a differential equation. And this opens up a valuable way to leverage existing results from the dynamical system literature. And what I'm going to talk about today falls into this category, and it's our work on neural Laplace, which greatly expands the representation power of existing neural differential equations. So just as a brief introduction for neural differential equation. So in general, neural differential equation learns the unknown differential equation with a neural network. And this is all done in a data-driven way. This type of model naturally handles irregular sampling frequency and has achieved state-of-the-art performance on many healthcare time series benchmark data sets. However, there are many different types of differential equation, and our quest is to design a single model to capture many different types of differential equations. And to see this, perhaps the most familiar and basic differential equation is an ordinary differential equation. And this is where the neural ODE comes into the picture. However, we also have a large number of other broader class of differential equations for which neural ODE cannot model or describe. And for example, the delayed differential equation, which has the equation explicitly depending on a previous state, and also integrate differential equation, ODE with external forces, and stiff ODE. These differential equations capture more general temporal dynamics, which are beyond the modeling capacity of an ordinary differential equation. And these more general class of differential equations are indeed needed in medicine and healthcare. And we have seen many examples, for instance, in PK/PD modeling, in epidemiology and bioengineering, that people do use like this broader class of differential equations. And in this work, we will take a holistic approach and propose a generalized unified framework, neural Laplace, that can learn all of these range of differential equations. And importantly, the modeler do not need to specify which class of the differential equation to learn a priori. So rather with the same framework, this neural Laplace method can capture all of these equations implicitly. And the trick is, unlike the neural ODE or existing neural differential equations, which models the differential equation in the time domain, our neural Laplace model leverages the Laplace transformation and model the differential equations in the Laplace domain. And so this brings two immediate advantages. First, many classes of differential equations, including delay and integral differential equations, can be easily represented and solved in the Laplace domain. And secondly, neural Laplace bypasses the numeric ODE solver and constructs a time solution using global summations, which means it has advantage at inference time. However, as we can see here, that in this illustration, the Laplace representation involves singularity points, which is also known as pole points, which means that modeling this representation directly with a neural network can be challenging. So in order to account for this challenge, we leverage a Riemann stereographical projection of the Laplace representation. So this stereographical projection is a quite simple projection from the complex plane to a sphere, which has a bounded domain. To learn the we use the neural network to learn the representation after the stereographical projection. So neural Laplace architecture involves three main components. We have an encoder network that learns and to infer and represent the initial condition of the trajectory. And we also have a Laplace representation network that learns the solution of differential equations in Laplace domain. And finally, we have an inverse Laplace transform algorithm that converts the Laplace representation back to the time domain. And this is an illustration of the block diagram. In many experiments, we have performed experiments on a variety of different dynamical systems, and neural Laplace achieves low prediction error on all cases with irregular sampling in mind. And here you can see some of the trajectories generated by neural Laplace, and here are more examples. And we have also released a code library that is available in Python, and you can essentially try the model out with just a few lines of code. And if you're interested to know more, please check our paper and visit the code. And we hope this work provides a practical framework to learn complex dynamics from irregular data. Thank you.
So thanks, Andreas. As Andreas mentioned, my name is Fergus Imrie and I'm a postdoc in the Van der Schaar lab. And I'm really excited today to be presenting some recent work from our lab on individual treatment estimation over time, called Continuous Time Modeling of Counterfactual Outcomes using Neural Controlled Differential Equations. So to begin, I want to just introduce the setting we're in, and I want to do this via an example. So let's suppose we have a patient with lung cancer, and we observe a series of observations for that patient and the associated treatment decisions made over time for this patient. What we want to do now is to infer what will happen next for this patient under a future sequence of treatments. And in order to do this, we must estimate counterfactual outcomes for this individual given their history. And we really want to be able to do this for multiple different treatment plans, such as no treatment at all, or any arbitrary series of treatments. And we want to be able to do this so that we can help doctors answer what-if questions, such as whether to treat this patient, how to treat this patient with which series of treatments, and when these treatments should be administered. It's well known in medicine that timing is often very crucial. Existing work for this problem, though, has been limited to fixed regular time intervals between observations. However, in the real world, observations typically aren't at regular times, but instead both the patient's history is observed irregularly, and we wish to evaluate future treatment plans that might occur at arbitrary time points in the future. So the key question becomes now, how can we learn from such observation patterns? In Zhaozhi's talk, he discussed several recent advances in time series modeling that I'll briefly summarize again here, since we'll use them later. So historically, recurrent neural networks, or RNNs, have been the most popular class of method for handling time series. However, as Zhaozhi mentioned, they only really regularly handle regularly sampled time series. And this is primarily both due to the assumptions, but also the fact that the latent state of these models doesn't update except at observation points. Modified recurrent neural network architectures have been proposed to try and address this, in particular around this kind of latent update. However, these still suffer from issues in the irregularly sampled setting. More recently, this new class of models called neural differential equations have been invented that enable us to tackle irregularly sampled observations in a much more natural fashion. And this occurs by modeling differential equations using these models and learning how the latent state should evolve as a function, so that we can access this at any time point between observations. In this work, we leverage these insights and advances and propose a solution for this problem in the irregularly sampled setting. And that is the treatment effect neural controlled differential equation, or TECDE for short. And our key idea is that we want to learn a continuous latent representation of the patient state as a solution to a controlled differential equation, or CDE. Our method works as follows. So first, we encode observations that have been made historically up to time t and learn a continuous representation, or latent state z, as a function of these observations. Then for some future plan of treatments, we update this latent state according to a second controlled differential equation. And then we use this updated latent state to predict counterfactual outcomes. One key challenge in treatment effect estimation over time is that of time-dependent confounding, which can bias the treatment assignment. To briefly explain what this is, this happens when patient covariates are affected by the past treatment decisions, which then affects the future treatment decisions and indeed the future outcomes as well. And in TECDE, we address this via domain adversarial training. So as Alicia mentioned, with counterfactual estimation, we can't actually observe the counterfactuals with real-world data. And thus we need a simulation environment in which to assess both our method and other methods for estimating treatment effects in the irregularly sampled setting. So for the underlying dynamics, we use the model for lung cancer tumor growth by Geng et al., which models the effects of both chemotherapy and radiotherapy treatment on tumor size. We then create a flexible simulation environment by introducing a continuous time process parameterized by a Hawkes process. And this process has two key features which motivate our adoption of this for our simulation environment. The first is that the process is self-exciting. And what this means is that after we have made an observation, we're more likely in the short term to see another observation for a given patient. And in addition, this process is state dependent. And in our simulations, we base the kind of state factor on the American Joint Committee on Cancer's cancer staging system in order to model the effect that patients with more severe disease are typically observed more regularly than patients with milder illness. So we now benchmark our model, and we observe that across a range of scenarios within this environment, TECDE outperformed existing state-of-the-art discrete time baselines actually developed within this lab, CRN and RMSN. In addition, we demonstrate the importance of the domain adversarial training portion of our method by comparing TECDE with a version of the method without this component. Finally, we show the utility of TECDE both for counterfactual estimation, also for treatment accuracy, which is measuring how likely we are to select the optimal treatment in a given scenario. So to briefly summarize, in this work, we've extended counterfactual estimation over time to the irregularly sampled setting and introduced a simulation environment for irregularly sampled observations in order to assess solutions for this problem. We've proposed TECDE as one solution, modeling for the first time a patient's latent trajectory as a solution to a CDE, leveraging advances in neural differential equations. We've demonstrated the utility of our approach both counterfactual estimation and treatment accuracy. I'd like to thank my co-authors, Nabeel Seedat, Alexis Bellet, Zhaozhi Qian, and Mihaela van der Schaar for this work. And if you'd like to learn more, please do read our paper or ask me questions during the Q&A session. In addition, I want to highlight that we've open sourced both our code and our simulation environment. So do check that out if you're interested. And finally, on behalf of all of the authors, I'd like to thank our various funders. Thank you very much.
Great, yeah, no, thank you, Andres. Hello, everyone. I'm Alex, third-year PhD student with Mihaela. Normally, I work on safe and robust machine learning systems in a sequential decision-making setting, but today I'm going to talk to you about a more applications-based project that we've been working on called synthetic model combination, and in particular, how it was inspired by and can be applied in pharmacological settings. So this talk will revolve around a paper that's been recently accepted in Europe this year called Synthetic Model Combination, an Instance-Wise Approach to Unsupervised Ensemble Learning. The first question being, okay, what is unsupervised ensemble learning? Well, if we kind of work through it backwards, we have learning, which, I don't think will be too surprising to this audience. Then we're going to have ensemble learning, which is to say that we want to learn some ensemble of crucially multiple models that we will combine to make predictions. And finally, unsupervised ensemble learning, which means that we don't have any labeled training data that we can use in order to train or fine-tune the models that we have. So the task is essentially that, given a bunch of pre-trained models, how can we construct the best ensemble without using any labeled data? It's obviously quite challenging without any extra information. So to go forward, we'll have to make some assumptions. There is some information about the training context distributions available to us that we can then use to have a better idea of which models might be better than others when it comes to making predictions for a given instance. So yeah, in particular, now, while this is obviously not the most common form of problem faced by machine learning practitioners, there are plenty of scenarios from finance to medical sciences and even consumer practice, where stakeholders have developed models on private data that they either can't or don't want to share. And we may be left with the question of then, how do we use these models that have been developed and published without their corresponding data? Here we're going to highlight a specific use case based on an upcoming paper focused on pharmacometric model ensembling, which we have worked on with Richard Peck, formerly of Roche, who's now actually recently joined the CCM, as well as Megan Gibbs of AstraZeneca. Here we look at population pharmacodynamic, or PopPK models, the differential equations that model the concentration of a drug in the blood of a patient. And it's important for us to accurately measure this while doing so in order to keep drug concentrations within therapeutic ranges. We'll usually be interested in the area under the curve, that is this area here. Oh wait, why is that going? That's this area here. And essentially, it's a measure of total drug exposure. And if we have an accurate model of what this will be, we can better adjust doses given to patients to hit these target AUCs. The thing is, there are often many published and competing models for the same drug. Since, as I said previously, the private medical nature of this problem means the data on drug response in humans is definitely not widely available. So new models can't be really trained on the data of the previous models. These data sets that the models are built on are often relatively small and focus on a specific subpopulation, such as those of a particular hospital or suffering from a specific comorbidity. So the question really happens to be, what do we want from these models when, for example, we have 3 models, one from an ICU, one based on some middle-aged women patients, and one on a retired population. And then we have a case where a new patient, who's potentially a young male, comes in, and we want to make some predictions. Well, some naive methods will just take all of the models and simply weight them all equally, or at least not according to anything specific about the individual that's come in. What we want, though, is sort of to be able to adapt the weights of the ensemble that we construct to this specific instance. For example, a new patient may be much more similar to the cohort of the first model in the ICU than to the other cohorts, and thus we may want to place more importance on that model's predictions. So if we take a kind of more specific look at vancomycin, there is a huge number of existing PopPK models available. And we sort of, in the paper, we follow a lot of the work of Astra et al. Here in focusing on 6 models, each from a kind of separate, quite disparate subpopulation. We have extremely obese patients, those critically ill post-heart surgery, some trauma patients, some from the ICU, septic, and just generally hospitalized patients. Now, in our approach, we first acknowledge that there is actually a large amount of information left on the table when making predictions with existing model averaging methods, such as the ones they use. In particular, all of these models come with significant information about the training demographics, inclusive of age, sex, height, weight, and serum creatinine levels. That can be pretty useful information for which models will be relevant for new test cases. So the approach we're going to take is essentially to learn some representation of individuals, where we can model regions of the space where we think the models that we have on hand will work well, and where we think they will not. To do this, we're going to need to take advantage of this cohort demographic information in order to really inject structure into this latent representation. We can see here how for different test cases, based on where they are in this latent space, we want to construct new and different ensembles for predictions. Now, in order to learn this representation, we use a kind of autoencoder style architecture to learn a latent space, but where we'll induce some additional structure with some extra surrogate losses. First, we kind of have a standard reconstruction loss here at the top with two parts. One that ensures examples reconstructed from the latent space are accurate, and one that sets a kind of minimal prior on their location. Then we have a kind of more interesting parts, which are connection separation losses, which manipulate representative examples we produced using the associated demographic information that I've just kind of previously said we've got available. These losses kind of both measure a distance between representative examples, with the connection loss aiming to move regions together where the models agree on predictions. The intuition being essentially that predictions are correlated. It's most likely because they both know the right answer rather than just randomly being wrong in the same way. And this works especially well when you have a kind of very large predicted space. The separation loss, on the other hand, repels different models by default, encoding kind of prior that the models come from separate and like disparate demographics. Now, at a high level, then we begin by estimating densities and representative examples from the demographic information available. Using this along with the test set features we wish to make predictions over, we'll learn a new latent space and the corresponding test latent representations. And given these representations, we calculate a per instance ensemble based on their presentation in the latent space with respect to our representative examples. At prediction time then, especially here for vancomycin as an example, we can proceed by first making predictions using all of the individual PopPK models available to us in this green region and in this gray region. Using whatever software we like, non-mem being seem to be the program of choice among pharmacologists. We can then calculate our latent representations and use them to estimate their density under our existing models and calculate their relevant weights. An extra point I haven't mentioned yet, and is explored more in our pharmacology paper, is that we can incorporate weights from model averaging algorithms, such as Bayesian model averaging. We don't vary their predictions by individuals, but given the fact that their calculation is based on factors that are completely different to what we do with SMC, they can also be used to help performance when we have that little bit of extra information. And yeah, just to kind of, based on that kind of extra model averaging part, and placing SMC kind of within the kind of currently related literature, we can see that if we look at it based on the information available to at test time, first we have naive averaging where none is available, or far on the left, and then with some label validation examples, we can employ those methods such as Bayesian model averaging that kind of use some small subset to kind of estimate performance. We can then go on to kind of consider transfer learning and domain adaptation, but those usually require quite a bit of at least kind of some feature examples from all the different places. And in the extreme case, when we know all the data, our best bet is probably to train new models using all the available information. SMC sort of just slots right in here, where we have no level data, but some demographic information available. Now, moving on to kind of results with vancomycin, we're predicting our AUCs. We can actually see that we do a pretty good job, especially when we have a couple of data points per each patient, showing improved performance over all the individual models as well as a kind of naive ensemble. We can see that we aren't getting everything for free though, and in cases where there is actually kind of a wide variety of results, for example, pretty poor accuracy from this model, SMC will sometimes still incorporate those predictions because it doesn't essentially know better, leading to slightly deteriorated performance. But in cases where all of the models tend to work kind of okay, but mostly focused on their own domains, we can see that we can combine those in a much more effective way to get high performance. So, I mean, I see key takeaways here. We aim to show that we can really improve predictions without any labeled data. Just knowing where our models came from is enough. And there are lots of potential opportunities in particular that we can use to help precision dosing in pharmacology. And one of the kind of key things we might be thinking about in the future is, can we move any further to the left in the figure that I showed previously? And can we do anything without this demographic information? But that seems to be a very challenging problem indeed. Thank you very much for listening. If you'd like to take a look at our paper and code, please follow these links. And I'd just like to give some additional thanks to Microsoft Research for sponsoring my work. Thank you all very much.
So hello everybody, my name is Jeroen Crabbé. So I'm a third year PhD student at the Van der Schaar lab, and today I'm very happy to present this work about concept-based explainability. So without further ado, let's give the outside. Oh, before the outline of the talk, I just want to say what I'm going to talk about today is really the tip of the iceberg, because I'm only going to talk about concept-based explainability, which is really some part of the work we have done in the lab. We have a lot of work on explainability, so feature importance, interpretability of unsupervised models, example-based explanations, and I'm going to only cover, like concept-based explanations today. So bear with me; it's not everything we have done in this area. Of course, I should also advise to read these two very interesting. So one is a paper, and the other one is an article, both by Bing Kim, and she's really like the person who invented these concept-based explanations. So if you want to know more about this, I really invite you to read these two very interesting papers and articles. So let's talk about concept-based explanations. What do I mean really by concept-based explanations? Well, maybe I think it's good to first start by defining what I mean by concept. A concept is simply something that is defined by the user, and the way the user defines concepts is by just providing positive and negative examples. So imagine I want to define the stripe concept. Well, I could just take images of stripes and call them my concept positive images that illustrate what the concept is. And then I have images that are concept negatives that don't contain stripes. So they illustrate what the concept is not. So in some sense, you can kind of consider a concept as a binary human annotation on the examples that are fed to machine learning models. So each of the example either has or hasn't the concept in it. Of course, you need to be sure that like we can deduce the presence or the absence of the concept for the input features you can observe. For instance, it doesn't really make sense to talk about a sound concept if you only have images. So you need to be sure that you have the right modality to kind of define the concept you want to define. So what do we mean by concept-based explainability now? Well, we simply start with a typical, like a neural network that predicts, images, like the label on images, for instance. And the user that uses this neural network could say something like this. I myself, as a user, I kind of recognize the zebra on this image by looking at the stripes, right? That's kind of a characteristic of zebras. Stripe is the concept. So I want to be able to kind of know if the neural network is using a similar concept in order to identify that this image contains a zebra. So is the prediction sensitive to the stripe concept? That's the kind of question we are interested in answering when we do concept-based explainability, probing this neural network through the lens of concepts that are familiar for us human beings. Of course, it doesn't need to be images. You can also have patient features. And for instance, a prostate cancer mortality predictor here. And likewise, you can really probe this neural network by asking a question like, is the prediction of this mortality predictor sensible to prostate cancer grading system? So the prostate cancer grading system is a medical concept, and the doctor might want to probe this neural network by using medical concepts. That's also possible to do that with concept-based explainability. So the main way in which people do that in the literature, so before our work, is through what we call concept activation vectors. So I'm going to quickly explain how it works. So you start really with your positive set of examples and negative set of examples, and the neural network you want to express or you want to explain. So in this case, like the neural network that predicts the probability of observing a zebra on the picture. And what you're going to do is you're going to actually just probe at the representation space of this neural network. So for instance, you take a slice of the penultimate layer and look what's happening inside. What you are going to do is you're going to map the positive and the negative set of examples in this representation space and kind of observe how each of these are distributed according to, like with respect to each other. So let us take a zoom on what's happening in this representation space here. Well, as you can see, I can actually linearly separate my positive and negative set of examples. So I can draw a hyperplane like this. And like all the positive will be on the side and all the negatives will be on the other side. And once you have something like this, you also have a vector that is normal to this hyperplane. That's what people call concept activation vector. And the reason why it's called like this, it's quite simple, actually. If you look at the image, it's just pointing in a direction where the concept positive examples are kind of grouped together in this representation space. Well, now that I know where the concept positives are, what is the direction that encodes concept positivity, I can just compare that to, like the probability, for instance, the gradient of probability of observing a zebra. So, the direction of the latent space in which the probability of observing a zebra increases. And I can see that these two vectors kind of point in the same direction, which kind of indicates that the model relates observing zebras with the stripe concept in this case. So all of this is really cool, but actually I made a big assumption here. I kind of assume that, concept positive and concept negative examples are linearly separable. What if I have something like this, in which, concept positive examples are kind of still grouped together, but they are not really linearly separable from the concept negative examples? Well, in this case, we need what we call concept activation regions, and that we have introduced in this NeurIPS paper that is going to be published soon. So the idea is the following. I can just take this example here, and I can just divide my latent space in two regions: the concept activation region that contains the concept positive examples, and the rest of the concept and the rest of the latent space, so that contains all the negative examples. That's a very simple idea. And we actually formalize this in our paper by using the smoothness assumption of semi-supervised learning. So more formally, I mean, it's like you kind of consider that, like a concept is well encoded in the model representation space if the representation space is smooth with respect to the concept label. So there is kind of a region of the latent space that contains most of the concept positive examples. There is one that contains most of the concept negative examples. And if you want, both of these regions are kind of well separated in terms of clusterability. If you use this definition, you can really convince yourself that linear separability. So if you have linear separability, you also have concept smoothness. So this more general assumption that we make, but we don't need linear separability to have concept smoothness. So in that sense, concept smoothness generalizes linear separability. So I'm not going to go into full details on how we actually define these concept activation regions precisely, but that's actually based, on this concept density that we introduced in the paper, that kind of measuring, how much the concept is represented in the point of the latent space you are observing. And by using that, you can also, by using this concept density that we define in the paper, you can define a kernel classifier that identifies, concept activation regions. I'm not going to go into full details. Of course, all of this is in the paper. Once you have that, you can also define, concept TCAR score, which actually tell you how classes are related to concepts. So for instance, how the class zebra is related to concept striped. That's actually in this way that you can define, you can kind of measure the link between the classes of your models and the concept that you have defined. And also, we can also use this kind of concept activation formalism to define feature importance scores that are specific to concepts. Also in the main paper, I'm not going to cover that in the details here. So, something more important I think it's worth discussing is like, okay, we have allowed to have non-linear separability between concept activation regions. So HC and H non-C are non-linearly separable. Is that really useful to have this generalization? Well, in the paper, we show that by kind of allowing this to happen, you have more precision in the way you capture, like the concept activation regions of the latent space. So in some sense, you need this what the experiment shows is that you need this nonlinear separability to kind of capture how the concepts are distributed in the representation space. If you want to do that more accurately, you need this nonlinear separability. Also, like using this formalism leads to global explanations that are better, in better agreement with human explanations. So better with respect to human, what humans would expect by looking at the model. And they also bring consistent feature importance. So we validate also like feature importance that are concept specific, and we see that it actually makes sense in the main paper. If you want the details of this experiment, of course, everything is in section 3 of the paper. So I would like to maybe like bring your attention to a last thing that we study in the paper. It's actually a use case of all of these concept activation explanations that I've been talking up until now. And the idea is actually, we could actually use, like concept activations and concept explanations to probe machine learning models in a bit of a more scientific way by just probing them by using scientific concepts. And the use case we did in this paper is the following. Like when you talk about prostate cancer, doctors use 5 grades to kind of determine the likelihood of the cancer spreading. And you can consider these 5 grades as 5 concepts that can be either present or absent for each of the patients you're looking at. And now you can train a deep neural network to kind of predict the mortality of prostate cancer patients. And you can ask the question as a doctor, like, are these concepts, the 5 grades, well encoded in this model representation space? And the answer to that is actually, we show in the paper, yes. You can have like concept activation region classifiers that generalize very, very accurately. And also, we show that in the paper that in this representation space, higher grades is associated with higher mortality, which is perfectly consistent with what doctors would say, because the higher the grade, the higher the likelihood of the prostate cancer spreading, and of course, the higher the chances of mortality. So that's kind of reassuring, and that's a way to kind of probe this, model by using scientific concepts. Of course, this is only an example, and I think that there is a lot of potential on, like probing these machine learning models with scientific concepts in order to have validation, beyond plain test accuracy. I think it's more interesting to kind of look a bit deeper what's happening inside these models. I should say that there are a lot of things I have not covered in the talk due to time limitations, but by all means, if you are interested in any of these points, please read the paper. There are a lot of pages written for each of these points. I thank you for your attention. I hope you enjoyed the talk. If you want to learn more about this and our work, like you can follow one of these readings or the code base of the lab, different papers that we have written in Interpretability, and also my website where I kind of put all of this. I also thank Aviva for funding my PhD and especially this work. And also, we know you're going to hear a bit more, I guess, on the code part of things because Rob is going to present you kind of the code base we have implemented for interpretability. Thank you for your attention.
Hello, everybody. My name is Rob Davis, and I'm a research engineer at the Cambridge Centre for AI Medicine. And today I'm very happy to share with you the extensive suite of ML interpretability methods that we have developed. Okay, so in medicine, we need to go beyond post hoc explanations of static predictions. We need interpretability methods for time series, for patient trajectories. We need unsupervised learning methods explained, which are used for patient phenotyping. We need heterogeneous effects estimations for personalized therapeutics, and concept-based explainers like we've just heard about to discover new clinical concepts. And to effectively debug clinical models, we need to explain why some features or examples are important. We need to indicate when to be skeptical about the model. And we also need to adapt to your knowledge as the user to give you the explanations that are most meaningful to you. Okay, so, and that is to go from this situation where we've got a mortality prediction on Bob that's explained generally to one that is specifically targeted to Bob's clinician, so you can get the best prognosis and the best treatment. Okay, so at the Schaar lab, we're developing this suite of different ML interpretability methods. The images in this slide are from the Interpretability GitHub, links at the bottom. Jonathan also had the QR code to just a second ago. This GitHub aims to gather together all of our methods alongside some key methods from the community, then explain when you can use each method, help you understand these methods maybe, and also implement them as well. So there are many different methods in our GitHub. These include those for tabular data, for time series data, for unsupervised methods, and recently a new addition that Alicia presented earlier on individualized treatment effects as well. All of these methods can be broken down into 3 different key groups that each provide a different type of explanation. And the first of which being feature-based explainers. This is where we can indicate the input features that were most important to making the prediction. We also have case-based explainers or example-based explainers. These are methods that show you examples that the model sees as being very similar to the input record, and so it will treat similarly to how it treated that one. And also the method that Jonathan has just presented on as well, introduced concept-based explainers. So this is where you can provide a concept and then see how important that was to the prediction. For the rest of the talk, however, we will focus on simplex. This is a case-based interpretability method that just slightly starts to bridge the gap to feature importances as well. So how does simplex work? If we have a test record that exists in some feature space, we can apply our black box model F to it, and we get an output Y. But in simplex, we also provide a corpus of other examples that exist in the same feature space. These can be from the data set used to train the model, or examples that the model has never seen before. Similarly, we can apply our model to them and we get some predictions. Simplex works by then using a mixture of these corpus examples that best approximate the test record to explain why a prediction has been made for a given test example. And the important thing to note here, however, is that simplex does this in the latent space. So that is, instead of going all the way and applying F, we stop short by just one layer and compare the similarities there in that higher, or potentially higher dimensional latent space. And by doing this, we're effectively peeling back the final layer of our black box and peeking inside to see how it's viewing our test record compared to our corpus. Okay, so here we see two examples of explanations that contain a mixture of our most important corpus examples. In the first example, we see handwritten digits. And yeah, we can see there's the three members of the corpus there with their learned importances. So we're saying that the model sees the test record as being 46% like the first member, 37 the second, 17 the last. How can we use this information? Well, to me at least, it looks like we're onto a winner in that we've got three examples of a digit 3, like our test example. So that's the first thing. They are of the same category, and so we do want the model to treat it similarly, which is what it's going to do at the moment. And secondly, we get to an insight into the feature importances here. So that's the red and green highlighting of the pixels, and you can see, for example, in the third example, the 17%, we've got a cluster of red pixels around the sort of flourish at the end of the 3, indicating that that is unimportant. Those pixels are unimportant to the model's classification, and so by examining features like that and delving into the details, we can see, do we agree or not that the model is prioritizing the right things, that they are genuinely important. Okay, and below that we see another potentially more interesting example of simplex being used in a clinical setting. This is completely analogous to the first example, but we'll delve into more detail on that type of task in the demo coming shortly. So in summary, simplex unifies the case-based and feature-based explanations. It captures insights from the latent space, giving us an insight into how the black box is seeing our input records. And it also the user can provide the corpus. So that means that you can provide the most meaningful examples to you, be it, for example, canonical case studies that are written about in the literature, or the last 100 patients you as a clinician treated. Okay, so now you've been introduced to the method, I'd like to play a short video that shows off the user interface that demonstrates how the inputs, demonstrates how the outputs can be used in simplex in a bit more detail. Welcome to the Simplex Demonstrator app. Over here in the sidebar, we can see a couple of options. Let's jump straight into the tabular data. You can see in the drop downs, we can choose our data set. Let's leave it on the breast cancer seer data set, and we can choose our model as well. Let's leave it with the multi-layer perceptron. Of course, with simplex, we can use any model as long as we have access to the latent representations and any data set that model has been trained on. So if we select a new patient over here on the test patient slider, there are 50 patients kind of preloaded into the demonstrator. The model's prediction here is a breast cancer mortality prediction, and you can see it's predicted a favorable outcome. Underneath in the bottom left here, you can see the input features for the test patient. It looks like there are quite a few features, but that's the one encoding. We're in reality only dealing with about 15 features. Now you can see on the main area the corpus breakdown. So we provided Simplex with a corpus of different examples that exist in the same feature space as our test patient, and it's chosen a mixture of them that together best represent our test patient. So you can see it's saying our test patient is 66% similar to this person and nearly 32% similar to this person. Together, that doesn't add up to 100%. That's because we're filtering out all of the lower percentage importance corpus members, but they are still there behind the scenes, and we can see them by lowering the example importance spider. Okay, so under each person icon, we see the model's prediction for that individual and the real world outcome as well. So we can see here whether or not the model was right, because these are historical examples. And then underneath that, we also see the input features for the corpus member as well. Now, the color coding here is the feature importance, and is where we sort of bridge the gap with Simplex between case-based explainability and feature-based explainability. If I click on the highest importance first, radio button in the sidebar, all of those most important features will rise to the top, and we can start to do a compare and contrast with our test patient. And so what we're doing is we're seeing this mixture of members of the corpus is very similar to our test patient according to our model. And we want to see, do we agree? Do we agree that these patients are similar? And do we want our model to treat them similarly? In doing that comparison, use these features to compare, and we can see the importances of those features that the model is considering. So if we do that very quickly, in this example, we can see 51 is similar to 45. That's sounds about right. And we've got a 48 over here, so that sounds good too. And if we scroll further down, we see 6th stage 2A seems to be important across the board here, and that does agree with our value here of 1. Okay, so let's have a look at a time series example. You'll notice everything looks pretty much exactly the same, but now we've got multiple time points for each value. And that also comes along with multiple time points for our feature importances as well. So we can see how the feature importance changes over time, which is quite nice. Okay, so in this example, we're looking at a prostate cancer data set, and we have an RNN as the predictive model, or specifically a GRU. So we could do the same job of looking at all of the values and comparing and contrasting, but there's one immediately interesting result that we can see on the screen here. Our test patient has been given a negative prediction, just the same as our most important corpus member at 53.5%. However, this corpus member in the real world had a positive outcome, so that prediction was wrong, and the model is seeing our test patient as being similar to this patient. So that calls into question, do we want our model to treat this similarly? Do we trust this prediction? When you're using Simplex in anger, you wouldn't necessarily have access to the real world outcome, and we didn't give it to the model when we trained the model, but we can see it here because we used historical examples. So we can check this box to see the real world patient outcome and see that, in fact, yes, exactly the same thing did happen. And so we were right to be a bit nervous about using this prediction. That about wraps it up for the Simplex demo. Thank you very much for listening. Okay.
Maybe I can take this opportunity to thank you again very much for sponsoring our research, and really providing us with all this support, and really to advance this work of machine learning in medicine. I really hope you enjoyed the presentation of the various students. I'm extremely proud of them, and I hope that you also enjoyed it. Please reach out to me with any feedback or any comments, or anything we can do to further make this research useful and valuable to you. Also, if you have questions about specific presentations or topics that we have not covered or we have covered but not in enough depth, or if you want to take these methods to your data sets, or you know of others that have such data sets that could use these different methods, please let us know. Thank you very, very much for your time and for joining us today.